Silence, please. Silence, please. So we are coming to the first speaker. First of all, let me thank you for the very nice opening session, for the music, for Walter Kuchera's very interesting and spiritual talk. Okay, we are coming to the first presenter, which is Laura Catting, who will present us a new system for REM pyrolysis oxidation, 14 CO2 analysis of sediments.
Yeah.
Please go on, 12 minutes.
Yeah, thank you very much. Welcome everybody. My name is Laura Catting. I'm a PhD student at the Alfred Wegener Institute in Bremerhaven. And as part of my PhD project, I'm establishing a new method called REM pyrolysis oxidation in our lab. And today I will show some of the most recent progress that has been made in this project, and I will also show some of the first results that we received for an interlab comparison that we initiated. But first, I would like to talk very briefly about the method itself. So what is REM pyrolysis oxidation? Pyrolysis itself refers to the thermal degradation of a substance in the absence of oxygen. In our case, that substance is sediment that has been acidified to remove any inorganic carbon. And this sediment is then heated from 25 degrees to about 900 degrees, which leads to the formation of volatile pyrolysis products, which are subsequently oxidized to CO2, and then this CO2 can be radiocarbon dated, either as gas or as graphite. And what you see here is, you can't really see the pointer. Well, anyways, on the left side, you can see the result of a typical RPO run. It's called a thermogram, and what you see is the CO2 that is developed in dependence of the temperature. And the underlying assumption here is that labile organic matter that has a lower thermochemical stability will react at lower temperatures and also form CO2 at lower temperatures compared to organic matter that is more stable and will react at higher temperatures. So based on the shape of this curve, we can identify fractions of organic matter that have distinct characteristics. And if we manage to trap the CO2 from this fraction separately, we can then radiocarbon date it separately, and in this way we receive multiple radiocarbon ages for one single sample. And what we typically get is the stepwise increase of the radiocarbon age with the temperature. So the radiocarbon age of a fraction collected at higher temperatures is usually much older than that of a fraction collected at lower temperatures. This is the very first RPO machine that was built in 2003 at the Woods Hole Oceanographic Institute. It is now located at the University of South Florida, and it served as the prototype for the 3 systems that were built in the following decades at NOSAMS in the US, in New Zealand, and in Northern Ireland. Then 2 years ago, the MPI in Jena bought a commercial machine. It's the same one that we are also using, and they modified it for ramped combustion. So they don't pyrolyze the sediment, they combust it. And then last year, the Knife Radiocarbon Lab introduced their system. It's also a customized system that they built themselves, but it's different. It has a different setup than the other ones. And they also use it for ramped combustion. Apart from these, let's say, established systems, there are also 2 machines that are currently being developed. One is at the ETH in Zurich, and one is our system at AVI. Here you can see the main part of our system. It's a commercial machine we bought from Elementar. It's called a solid-top cube, and it's initially used to separate different species of carbon within one sample. This is what the inside looks like. Behind the shield, the center part, there is a quartz glass reactor that is located inside 2 furnaces, an upper pyrolysis furnace and a lower oxidation furnace that is filled with an oxidation agent, in our case that is copper oxide, and a platinum catalyst. On top, you can see this round, darker little thing. That is where the crucibles that contain the sediments are located. And then the upper rising part is the autosampler. The autosampler grips one of the crucibles with the sediment and then lowers it into this pyrolysis furnace. and this upper pyrolysis furnace is also that part which is dynamically heated. The pyrolysis products are carried with the gas stream down to the oxidation furnace. They're oxidized to CO2, and then the CO2 passes from here through this chemical trap that contains brass wool. Is it working now?
Yes. Just a second.
It's fine. That removes the halogens, and from there the gas stream goes into the water trap, and from there to the back of the machine where there is a CO2 detector. To the outlet of the machine, we have connected our self-constructed zeolite trap system. It consists of... Now it's working? Thank you very much. Yeah, no. Okay, it doesn't matter. It consists of 8 identical zeolite traps that are connected to a multi-position valve. And the whole system can be decoupled using this red quick fit connector. And this quick fit connector is gas tight when it's closed. But during the coupling and the decoupling process, because we really push it manually inside of each other, we always introduce a tiny amount of oxygen from a tiny bit of atmosphere into the system. And that's why we have the so-called waste trap. It's completely identical to all the other traps, but we guide the gas stream over this waste trap during the coupling process to avoid contamination of the fractions we have already trapped on the zeolite traps. This is what the system looks like in the lab. You can imagine the Solitox standing right next to it. And then the gas enters here to this 3-way valve, either into the atmosphere or through this tubing. And here you see the quick fit connectors onto our zeolite trap system. And then we can use this little remote here to choose the pathway of the gas. So if we conduct a pyrolysis run, we identify the fractions we want to separate, and then we use this little remote to guide the gas stream accordingly over one of these traps so that we can trap every single fraction on an individual trap. Once the trapping system is loaded, it's deconnected here and here, and then we carry the whole loaded trap system to our AMS machine, which is a Mikadas. You can see it there in the background. And then in front of the Mikadas, we have this ramp system. Here, inside of this little hole, you can see the outlet of our hot air heater that is used to liberate the CO2 from the traps. And then we have several little hooks here that we can use to move the trap up one step if we want to measure the next trap. So, now I'm with the trap system.
Still rolling.
Put a thermocouple in front of the heating system. Then we turn on the power and the air that is used for heating and cooling. And then I move from the waste trap to the first trap. And then I start the heater, and you can't actually see it right because I'm holding the cable so nicely in front of it. But I will move them in a second. So now you can see the heater is working pretty quickly. We reach 400 degrees in about 1 minute. And this heating process then liberates the CO2 from the traps, and the CO2 is carried from the traps through this tubing into the gas ion source interface from the Mikadas, and from there directly into the gas ion source when we do the 14C measurements. Now, the fact that we measure our 14C as gas, our CO2 as gas, and that we use it in combination with this zeolite trap system saves us a lot of time because we don't have to graphitize our samples and we don't need a secondary combustion step. So if I get a sample that I want to analyze and have never measured it before, I need to conduct 2 pyrolysis runs, one to identify the fractions and then one for fraction collection. And then we need 15 minutes 14C measurement time for each fraction. So let's say if I trap 6 fractions in one sample, that would come up to a total of 4.5 hours, including the measurement time. So if I can load both trap systems the day prior to the measurements and then continuously load the system that is not currently being measured, I can measure up to 33 fractions per day, which equals to about 2 to 5 samples. Here you can see a typical RPO run that is generated by our Solitalk. The Solitalk can do both combustion and pyrolysis. We usually use it in pyrolysis mode. But even in pyrolysis mode, there is a time towards the end of the measurement here where the system introduces oxygen to burn off any organic material that cannot be pyrolyzed. So we create this non-pyrolyzable peak, which is usually the highest peak in the thermogram. We create it always, and that's regardless of the nature of the sample. Here you can see the first results of our blank determination. To do this, we pyrolyzed different masses of a modern and a fossil standard, and then radiocarbon dated the 14C. And then the 14C values are plotted over the inverted mass, and a Bayesian linear regression model is applied to calculate the blank, which is determined by the intersection point of the 2 linear regressions of each standard type. And in this first attempt, we achieved, or the result was, a blank with a mass of 3 micrograms of carbon and an F14C value of 0.46. And with this initial blank, we could then start to think about an interlab comparison. Here you can see some characteristics of the systems that I introduced to you earlier. This letter here denotes which reaction type pyrolysis...
1 minute.
Oh, 1 minute. Oh, sorry. Okay, I'm going to skip through that a little bit. Anyways, let's just say the ABI and the ETH systems are the only ones that use zeolite traps instead of cryogenic traps. And our blank is in the overall size range that has been published in the literature so far. For the lab comparison, we sent out different sediment types to the labs and asked them to return the thermograms and asked them to measure and blank correct the data. They would measure anything in their labs. And now I'm going to quickly show you the results of the Cow Creek and Arctic sediment that we sent out. Here are the results of the Cow Creek. What's really important here is to see that the thermogram from NOSAMS and the thermogram from New Zealand, they look very similar. And this is in contrast to the thermogram that we produce, which looks not only different in shape, but we also produce CO2 until a much higher temperature, until about 900 degrees. And if we look now at these results here, at the F14C results, we can see that we see a similar trend at the different labs, but there's a substantial difference in the individual ages we got for the fractions. And one hypothesis is that this is caused by the amount of oxygen that is included in the gas stream. I'm going to skip over this. These are other results, but I'm going to skip them now. Here you can see the thermograms we got for a different type of sample, and in order to investigate this hypothesis about the influence of oxygen, we decided to do some more experiments with this sample. This is our thermogram in comparison. You can see the shape is really different, and we have this super large non-pyrolyzable peak. And what we then did is we installed an oxygen sensor in the gas line, turned off the oxygen supply to the machine almost completely, and then started a combustion run. So not a pyrolysis run, a combustion run. The oxygen sensor measured the oxygen concentration in the gas stream to be about 0.1%. And this tiny amount of oxygen in the gas stream shifted our thermogram from this one to this one. So it basically replicated the thermograms we got from the other labs. And it might not be so surprising to receive different results when you use 2 completely different methods like pyrolysis and combustion, but at least to me it was extremely surprising to see the magnitude of this effect already present at this low amounts of oxygen. This brings me to my summary. We have established a working RPO system with a robust set of standard operating procedures at AVI. We have a low procedural blank, and we are now basically ready for routine operations. And as a first result from the interlab comparison, we can see that the amount of oxygen has an extremely high influence both on the shape of the thermogram but also on the radiocarbon date we receive. That concludes my presentation. I would like to take this opportunity to thank the project partners for their interest in this interlab comparison and for the time that they have invested. It's much appreciated, and we're really looking forward to receiving more data to fill in some more of the gaps.
Thank you very much. Well, if you want to do the competition. Thank you for your very interesting talk. Let's say one question because of the low amount of time, if there is. If not, Elisabeth.
Mm-hmm.
Not the background and not the oxalic or the standard. Do you have some results that you reproduce?
We have results. I haven't plotted them here, but we have measured one sample about 70 times, and we have a really good reproducibility. Unfortunately, I would like to show you the plots to prove that, but we have definitely looked at that, and this is one of the main concerns, to be able to reproduce our measurements, but that's one of the advantages of a commercial system, that it's much easier to reproduce the data.
We can continue this during the lunch break.
Yes.
Okay, let's continue to the next speaker. And thank you. This will be Mr. or Mrs. Bolandi. Mr. Bolandi, Organic Matter Dynamics in those lumps, insights from online ramped oxidation, 14C analysis. So we keep the methods.
Okay. Hello everybody, I'm Marco, and today I would like to bring you to a small journey specifically on the organic matter present in the permafrost and in the thaw. Something similar, a work that we did similarly to what actually Laura presented. We will use actually the lability of the organic matter inside of the permafrost and use this in order to analyze the 14C. So, thank you very much, Laura, for your great job in presenting. First, I think you're pretty familiar with this plot, and personally, I'm quite interested in the permafrost. You will see why, and you will also understand that it's quite serious to look at this. The thing is, the advantage that I have is that the permafrost has also a lot of organic matter. And the thing is, we can use radiocarbon to actually date the turnover time. The thing is that on one hand, we can either use compound-specific methods, and these are really precise and really good in picking specific compounds. But often they are labor-intensive. On the other hand, you have the bulk measurements, and they are really great because you have an average. And as you could also see from Laura's presentation, well, it's not totally true because the average doesn't tell us what's actually happening. So, how can we resolve this? It's actually through differentiating the organic matter by, for example, in our case, the thermal lability. We at ETH, we did a similar setup, but we actually worked through the online ramped oxidation system, the double trap interface, which was developed together with Daniele De Maria and with the IMS, low energy IMS. I will specifically focus for these talks and for the time only on the online ramped oxidation. So, and my colleagues tomorrow, please go, they are really great people, go to their presentation at 11 and 11:12 for the double trap interface and the layout. So I skipped that part. What is actually Oro? Oro is a combustion oven, and it has two ovens. One is the combustion oven, and the top part has actually the ramping oven. Here you can see it contains actually the silver instead of platinum and copper oxide. We go actually with a really high concentration of oxygen inside and helium, and also with a strong flow. You will see that there will be difference, so every RPO setup has its own thermogram, and it's also important for the internal reproducibility to understand this. Finally, there is the CO2 sensor, and then the double trap IMS coupled. I remind you, just go to Daniele for better understanding the double trap interface and the Lea for URS. So, clearly I'm more interested in the organic matter, not the inorganic carbon. So we usually remove it by doing fumigation. Then in order to get 1 to 0.3 milligrams of carbon, we have roughly 30 to 50 milligrams of material. And finally, this is what I do. And you can actually see here a bunch of data that I measured, and these were actually 2 samples. Usually I do 2 samples a day with the different fractions. So, why do we care actually for the permafrost? The example that I wanted to show you. So, it's 1,500 gigatons of material, and you also know that this is roughly twice the amount in the atmosphere. But the Arctic is actually warming twice as fast. That means that we have huge puddles or thawing permafrost, which are creating positive feedback because you have organic matter which is decomposing. So, how does it look like? Well, here we are close to Yukon. We are in the Yukon, northern Canada, northwest Canada, Alaska, and we are in the First Nation lands. And all the gray dots are actually all those slumps, how big they are and how they look. So this is actually an aerial view. And this is a 6-meter wall, head wall, where the top part is the active layer, 6 meters of exposed permafrost, debris, which then runs off to the Peel River. So this huge thingy actually became, it's only 25 years old, not the carbon that we will see later. This is roughly, so I did an estimate using Google Maps, this is roughly 4 to 6 times the castle that we are in, just to give you an approximation. And this is one of the gray dots. So, how do the thermograms look like? So, as you can see, the permafrost layer, debris, and runoff, they look pretty similar, while the active layer has more material coming out, but it doesn't have the same shape. Okay, that's a good indication. So we know that actually permafrost, debris, and runoff are connected to. But how does it look like with the 14C? The 14C shows clearly that, as expected, the permafrost layers and runoff, they are actually in line, while the active layer is pretty flat. Even though being old, it's still consistent. So the thing is, interestingly, we have this age, but that means that the material that it's coming out, it's mostly also going into the river. While the active layer, which I would like to remind you, is also the more richer in organic, it doesn't show to being a big import into those runoffs. So, what could we understand? We could separate the organic matter that we had from the permafrost simply by using a simple technique, using the heat as well. And we measured different fractions. So that's already a big step. We showed differences, and we could see that the active layer, which is the more biological rich and has more organic carbon, shows actually more material at 400, 450 degrees. Finally, the runoff has an age which goes to the Holocenes, which goes towards the direction of the permafrost, or the permafrost layer, which makes sense. But the question is, what's actually inside? So for us, we know that the permafrost is releasing a lot of material, but it looks like it's being transported. So the question will be, what's actually the material inside in these different thermal fractions? And to do this, we would like to use the GCMS using the temporal fractions. I would like to thank actually my mentors and the people, some of them are here, and the technical support, the fundings, and in particular also the University of Salento and SEDA to inviting me and being the second speaker. That was really kind. Thank you very much. And whoa. Anyways, so one more thing. So please, if you have time, drink the coffee, the Lecce coffee. And it's the iced coffee, and it's really, really nice. So please enjoy this. Thank you very much, guys.
And now, volare.
Volare, oh, cantare, oh.
Thanks a lot for your talk, and you were pretty much in time, so we have time for a few questions. Alex?
Did you estimate any cross-contamination between fraction after the zeolite trap?
Thank you very much. That's really a good question. We didn't see any cross-contamination. We didn't see any cross-contamination that we could say, yes, there is there. And maybe Daniele Della Maria will tomorrow talk a little bit clearer about this. But we saw that by reproducing it, we repeated a few times the test, and actually it was consistent with what we were having. Furthermore, we had also the bulk measurements, just to make sure that we were not screwing it up. And we could see that actually the weighted average, which I didn't put on it, was actually consistent with the bulk measurements that we got. Does it answer your question?
No, actually, from our experience with age, everybody do pre. Pre. Combust samples and go to the lead trap and throw it away. And when we try actually estimate it, we have a few promille contamination if we don't do this. So you don't have this possibility to do pre, actually throw away some fractions.
So we
do it twice.
So we do actually the cleaning in the traps. So each time we are cleaning with oxygen and helium. So we are flushing, and then we don't have any signal afterwards. Does it answer?
Thank you.
Thank you.
Maybe we can go on. Somebody else? Some more questions? Guasiara?
Hello.
Hello. Great talk, Marco. Maybe you had mentioned, but what method do you use when you were producing the thermograms? The previous talk mentioned that you use a little bit of oxygen and that changed the thermogram. And I wonder if you had a mixture of oxygen and helium as well. So, and how much was to produce these profiles?
Yes, thank you very much. That's actually a really good question. Also, what Laura was pointing out. In our case, we are using 18% of oxygen mole inside of helium. So we are relatively in high concentration. the thing is, when we work, so the next step, we are actually comparing with the university AVI to see what's actually happening. We could already see, in our case, that inside, so the internal reproducibility is there, but when we want to actually do it compared to the nosams, which are using pyrolysis, we need to adjust, for example, the oxygen amount and lowering, or also the masses. The other thing that I would like to point out is also that it's never good to do a peers to apple comparison. So sometimes we need to be careful that our setup is one way and the RPO is another way. So that must be really clear. So clearly, it's always really good, but yeah, that's just something that is always in my mind, just to say.
Thank you.
You're welcome.
Elisabetta?
So, because you're talking about ramping,
Yes.
do you think that this reaction is thermodynamic or kinetic? Like, how do you decide the time of ramping the temperature? Because the peaks are not separated. So somehow it seems that you might have a contribution of two different fractions, or am I wrong?
Yes, that's actually a really good question. So there are few factors that we need to consider while we do actually the ramping process, and that's actually when we look at the temperature rate. And fortunately, we can also toggle it to make sure that we are trying to deconvolute better the temperature, the kinetics. So the thing is, it depends a lot also what you want to look at. Clearly, in my case, because I wanted to show you the permafrost and how it's actually evolving, in this case we thought, well, we will go with the ramping temperature, which is consistent between all the different samples that we are doing right now. But in this case, we decided to go with the speed that we selected that was ideal to show the fractionation in this case. But you make actually a good point. Any other questions?
So, I think we are finished for now. Thanks for the two speakers for their contribution. And it seems and I just heard that the last speaker for this session, Madame Tisner-Laborde, will not give this, so it is removed. So we are now proceeding to the lunch break. So I wish you all a good pause and bon appetit. And we will come back 1 p.m. here. Try to be straight so that we can start right on time.
Let's move from the sediments we talked about this morning and go to atmospheric aerosol. Maybe most of us are very well experienced with such material, but let me just summarize the main feature of this kind of particles with the name atmospheric aerosol, or with the name particulate matter. We typically intend all those suspended particles in atmosphere. They can be solid particles, they can be liquid particles, but what all of them have in common is the dimension. They are very tiny, very small, and in particular, the most important for us are the smallest. So PM10 or PM2.5, PM1, because as the smallest they are, the, let's say, most dangerous or interesting for the effects they can have, they are. Their typical concentration in air, there are many different situations we can find, because it's true that we can find particulate matter also in remote sites, like for example Arctic or Antarctic. But we can, of course, find particulate matter also in very crowded context, like for example cities or deserts or other places where we expect a much higher concentration. Okay. Sorry. Okay, so they are produced in primary processes, but they are also produced as a result of secondary reactions. So there are some, we can recognize some physical sources emitting particulate matter, but we also have to acknowledge that all the concentration of particulate matter we find in the atmosphere is not due only to primary processes, but also as a result of something different. So compounds already present in the atmosphere that react coming to, again, particulate matter. As for the direct processes, we can recognize both natural processes, like for example, the marine spray, eruptions of volcanoes, the mineral dust from the desert wind, and also the combustion of biomasses. But of course, when we speak about particulate matter, also the anthropogenic processes are very important because they can be emitted, for example, by combustion of fuels, both in factories or also in, for example, in cars. And they are also emitted by, for example, very common operations such as switch on or lighting the oven in our houses. So why PM is so important? First of all, they are important because a high concentration of particulate matter in atmosphere can affect our Earth, because they can be inhaled, and a prolonged inhalation of such particles can provoke lung cancer, also cardiopulmonary diseases, and can also affect mortality. But they have an important role also in the environment and also for the global change. Actually, well, I'm not an expert, but I know that the real role of particulate matter in atmosphere forcing and affecting the global change is not clear yet. So there are several parameters to understand, and actually there is no consensus till now whether they have a positive feedback on the changing of climate or a negative feedback. So anyway, in order to try to solve this ambiguity, is important to measure and to understand their role. Okay. Particulate matter is composed of maybe all the elements that are present in the periodic table. Now here I will focus on carbonaceous aerosol. so carbon element and also on carbon compounds, because it typically represents the largest component of all the elements present in the PM that we can collect, because about 50% of particulate matter in urban contexts is made of carbon. Of course, it is present in many different chemical and physical forms. I'm not an organic chemist, but I know that the possibility to arrange these three simple elements, such as carbon, oxygen, and hydrogen together, are almost infinite. And we can find all these infinite combinations in particulate matter. Here you see the, let's say, basic equation for the total carbon present in the particulate matter, because we can consider it as the sum of the element, what is called elemental carbon, organic carbon, and partly carbonate carbon. I will neglect in my presentation the carbonate carbon, because here in Italy its presence is less important than elemental and organic. The two types of particulate matter are different with respect to their optical and thermal properties, which means that, of course, the elemental carbon, which is also called black carbon, is characterized to be very, let's say, powerful in absorbing light. And as for the different thermal properties, typically organic carbon evolves at lower temperature with respect to elemental carbon. As I told before, there are different emission sources, and here we have the main principal emission sources for both elemental and organic carbon, which are the wood burning, the natural emissions due to, for example, wind erosions or something like this, and also the combustion of fossil fuel. So it's clear that if we would like to understand the role of such carbonaceous particles for the health and also for the global change, we have to identify the emission sources. Because only if we identify the emission sources, we can improve the global change models, and we can also contribute to arrange pollution abatement strategies. I mean, it's true that a large part of elemental carbon, for example, comes from combustion of fossil fuels. And we know that. But it's important also to understand if this is the main emission source, or whether there are other important contributions, because some contribution can be lowered, some others, unfortunately, not. So radiocarbon by itself cannot tell all the story about the source apportionment, because we have to deal with the different techniques if we are interested in different elements. And for example, for sure, we have to combine other physical techniques such as ion beam analysis, PIXI and PIGI, but also some chemical techniques just to identify and reconstruct as much as possible the situation of our particulate matter. But now I will focus on radiocarbon, and what we can say is that we have to do some source apportionment for radiocarbon. We can either measure the total carbon or the EC and OC separately. Of course, it depends on our technology, let's say, and also on what we are interested in, because we can use a simple two sources model measuring the total carbon, and in this way we can estimate fossil versus modern contributions, or we can measure EC and OC, and we can apply a three sources model, and in this way we can estimate the natural versus anthropogenic sources. As I wrote here, pay attention. In the three sources model, we don't know everything. I mean, there are some parameters that are still, let's say, undefined. There are several papers describing and estimating them, but we really need to do some more works to establish these parameters. Which are the challenges if we would like to apply radiocarbon to such material? Well, PM is typically collected on filters, and here you can see a typical quartz filter on which the particulate matter has been deposited. Of course, we have to use materials for the filters that is transparent to radiocarbon, and the choice is, of course, quartz. When interested in applying three sources model, the organic carbon has to be separated from the elemental carbon. And this is not trivial, but this is really tricky, still tricky, because there is still debate on the most appropriate thermal particle for the separation. We can apply different temperature in oxygen and or helium atmosphere, but there's still no consensus on which recipes we have to apply, and so this is also a challenge for the future. And masses are very small, because if we are interested in PM10 or even in PM2.5, our quantity, our mass on the filter is not so big. And in addition, you see here a filter, okay? But as I told you before, our interest is to apply different techniques on the same filter just to reconstruct all the story of the particulate matter. So not only what about carbonaceous particles, but also what about, for example, silicon, aluminum, and all the other heavy elements. So typically the filter is, each filter is divided in 3-4 parts, and each part is dedicated to a single technique, a single measurement. And of course, the mass on the filter depends on the place where you are sampling. Because if you are in a remote site, you don't have a lot of particulate matter. If you, well, you see here, this filter is very dark, because it was collected in an urban context, so where you have a lot of particulate matter. But things change if you go to a remote site. And things change also if you are interested not only in total carbon, but in the separate organic or elemental carbon. So it's important to have a reliable way to deal with small masses. And of course, all of us know that there are different approaches that we can use. We can use gaseous ion source in the AMS beamline, or we can use solid sample sputtering ion source. This is a very simple model of our accelerator in Florence. It's a typical configuration, an NMS typical configuration made of 3 M-volt tandem accelerator. It is not a dedicated AMS machine, because we have to share beam time also with the IABA people, but okay, this is okay. And we have a solid sample sputtering ion source. So we have to deal, yes, with small samples, but with solid small sample. And what I would like to underline is that in our configuration, I can say that we are happy to have a solid ion source. in the sense that this source allows us to perform multiple measurements on the same sample. So we typically insert a sample, measure for a while, then go to the subsequent sample and go on, finish all the batch and start again. So in this way we can monitor the stability of the accelerator and of all the beamline for periods up to a few days. So here I present you Miss Marple, and Federica, who worked with us, invented this name that I find it very wonderful. So this is the Milan Small Sample Automated Radiocarbon Preparation Line, dealing with samples collected from particulate matter on quartz filter. So here we have, you read this sketch from right to left. So in the upper part on the left, we have the feeding with helium and oxygen that are first purified and then enters the main oven. So filters are inserted directly in the main oven. Then the CO2 evolving travels along the line. First travels across a sulfur and halogen strap. Then there is a succession of two thermal traps made of liquid nitrogen, and the different temperatures are achieved by changing the relative position between the coils and the dewar with liquid nitrogen in. So in the first trap, we collect the water and the nitrogen oxide. Then we first trap the carbon dioxide. We collected from the sample. We trap the CO2 to get rid of helium along the line, and then we transfer the carbon dioxide to either one of the two reaction chambers. So here I summarize most of the characteristics of this beamline. Of course, we are using materials that are intrinsically clean or that can be cleaned very well to be used in radiocarbon setups. So we are using quartz, stainless steel, calrets. Calrets is polymer used for O-rings, and it's similar to Viton. We are most used to Viton probably, but it's very interesting because it is characterized by a very low degassing rate, even at high temperature of 200 to 250 Celsius degrees. Of course, we are using high purity gases, and also we are monitoring the CO2 that is evolving from our samples by monitoring the combustion process with a non-dispersive infrared detector. Graphitization is achieved by the Bosch reaction, so reaction of carbon dioxide with hydrogen in the presence of iron as a catalyst, and to deal with a very small sample. Here you see some photos of Miss Marple. In the first photo, you see there the main oven, the traps with consisting of the liquid nitrogen dewars, the first trap for water and nitrogen oxide, and then the trap for CO2. And here you see our small reactor optimized for about 50 micrograms of carbon samples. So the idea is to let's say, perform the reaction forming graphite directly on iron already pressed in such a small copper inset. So we first press the graphite on the small copper inset, start the reaction, and then transfer the copper inset with the graphite on in our typical, here, I don't know if people sitting on this side can see in the bottom part, in our typical aluminum target holders for our ion source. So yes, some notes to finish with. Reaction rate, it's not so, well, it's pretty easy to deal with such small samples. But we have to keep in mind that, for example, a standardization of the procedure is really important to have a very stable ion current along the EMS beam line in the accelerator. And the standardization of the procedure already starts in the graphitization step. So, for example, we have experienced that the reaction rate for graphitization depends on how much strong the iron has been pressed. And the reaction rate also influences our, let's say, typical beam currents that we are extracting from the sample in the ion source. So it's, I think that it's really important to be in stable conditions when we measure in the accelerator, but as we all know, these stable conditions start well before in sample preparation laboratory. Of course, on the MS beam line, attention is focused on alignment of sputtering position with the ionizer, and here in the graph you see a sort of scan of the current, both 12 and 13C. We can extract with respect to different position of the ionizer with respect to the sputtered graphite. So, working with the new line, we checked, of course, the reproducibility by measuring primary standards. We checked the background, and you see here the background is not so beautiful. We have in mind archaeological applications, but we are dealing with environmental particulate matter samples where the precision needed is somehow not so important as for archaeological application. And of course, we also check the accuracy on secondary standards. So, for example, measuring C7 standard, and also particulate matter standard. Well, as respect with particulate matter standard, I have to say that it's not easy to check accuracy, because actually there is no, till now, a real standard reference material for particulate matter. There can be some hints from, for example, the last intercomparison campaign we performed almost 10 years ago, probably. Some of us can remember.
5 years old.
Oh my God, sorry. Anyway, so this is an invite. Let's try to find a consensus material for second standard reference material. Okay, so this is an example from the campaign. What next? The line is fully in operation. First measurement campaigns have been carried out, but we can improve the precision and we can improve the background for sure, and we have still to address the further challenges of resource apportionment. And thank you.
Yeah, unfortunately, the chorus there.
That's all. Thank you very much. I will put a good word with the people deciding for the award, okay? For you.
You use up all your time.
Sorry.
Some time from
Sorry.
other people. And no question. Sorry. If somebody wanna ask, you can ask her in a break. And the next presentation is Meher from
Yes.
Biogas. Okay, interlaboratory comparison for the C14 measurement of the biogenic carbon fraction in biogas and blends of biogas and natural gas.
Thank you. Yeah, good afternoon, everybody. My name is Harro Meijer. I'm presenting this on, also with all the co-authors that you see here, and all have been working on this project that you see, a Euromed-funded project called Metrology for Biomethane, and this was a part of it. And of course, the whole interest in biogases and biomethane especially has everything to do with the energy transition, with our worries about climate, and I think in this group I do not have to explain that much further, except that there is nowadays also quite a lot of, say, legal and economic interest in this, because of the European the energy CO2 emission schemes. You have to pay if you bring fossil CO2 into the atmosphere, but not if the CO2 can be pointed to be of biogenic origin. So this is no longer just a scientific effort, it also has to do with economy, and as soon as economy comes into play, you need standards and you need legal things and so forth. So this whole metrology for biomethane also had those aspects. But we, as simple radiocarbon people, didn't care too much about it and just wanted to see what we could do finding the percentage of biogas in a biogas natural gas mixture. So I will show a bit of this, the background. I will show the pre-treatment of the biogases and the mixtures and how differences in that can make differences in your result. Show the results, of course, and then some conclusions and outlook. All right, the principle would be no real surprise here. The 14C method for biofossil determination is simply determining the 14C content of a sample. You compare it to what 14C from a pure biogenic origin would be, and the fraction, the ratio of those is simply your fraction bio. Simple enough. And for renewable materials like the junk, the waste you see here, the radiocarbon is of course very similar to recent atmospheric 14 CO2 values. So the fraction that you got out of this very simple formula is 1, or if you will, 100%. On the other side, fossil material doesn't contain any 14C anymore, and you will find F-bio to be 0%. And the strength, of course, in this, the unique strength of radiocarbon is that only radiocarbon offers this very high 1 to 0 and very unambiguous selectivity. People have been trying simpler method, but they will never score as good as radiocarbon. So this is not a surprise, this is not new, it has already been widely accepted, and you can see that by the list of the existing standards. So here you see Stuff General bio-based products has a European and an American standard. Solid recovered fuel has a special one. Flue gas has one for plastics, and for rubber. All are standards. And from a C14 point of view, you would ask, why on earth do you need so many standards? Well, that's how this legal stuff works. You have to describe again and again how the C14 method works, and more especially how you have to pre-treat your samples in order to get to a good result. And that is also the reason why for these biomethane or biogas fuels, we need a new standard. The principles, of course, are the same, but the practical process of pre-treating gases is not well covered by any of these existing standards. And that was one of the subjects of the biomethane project. The rest was about trace elements inside the biogas that could possibly waste the burning process or anything else. That was not of our concern. We had the part that had to do with 14C. So our task was to develop a 14C-based test method for fuel gases that contain methane. And for that, we organized an inter-laboratory comparison for C14 labs. And requirements for the method are pretty simple, you would say. Huh? So the sample preparation should be suitable for all types of fuel gases. So, of course, methane, but also the non-methane hydrocarbons, so the higher alkanes, so to say. They usually also contain CO2. We have to also consider that, maybe carbon monoxide, maybe even other stuff. The requirement is that all of this need to go into your final sample. All the carbon needs to be included in the 14C measurement, and this is vital, especially for mixtures between biogas and fossil fuel. And the quantification, of course, needs to be done like between 0 and 100% biogenic carbon. Right, now here's the inter-laboratory comparison. We produced a set of 5 samples. 2 were pure or allegedly pure biogases, original biogases from Sweden. And then the other partner made 3 biogas, natural gas mixtures out of this, aiming at respectively 45, 75 and 95% biogenic carbon, so the whole range basically. And collection was done by RICE, a Swedish organization. VSL, the Dutch Metrology Institute, did the mixture very carefully and quantitatively. And we at the University of Groningen finally packed all this and distributed it and collected all the information from the results. And then the sample preparation, starting from this biogas until a final radiocarbon result, was done by 4 experienced radiocarbon labs in Europe. RICE made a GC analysis of the original gases, and you see here biogas D, that's one of them, and biogas E is the other one. You see it's mostly methane, obviously. There's a bit of CO2, and biogas E is very strange because it also shows a little bit of these higher alkanes, which is very untypical for a biogas. So looks as if there has been an addition of 2 to maybe 3% or so of fossil gas. If you compare the column for the natural gas and multiply it by 0.02 or 0.03, indeed you would end up with values like in biogas E. Biogas D is mostly manure and 10% of other stuff, and biogas E is food waste and sludge. So both of them are very recent and short-lived material. Then the blue column, or the blue table here, shows the production of the mixtures by VSL, so very carefully done, such that we can determine the percentage of bio-C, so for all the molecules together, and you see the numbers that we end up to there. Then the 4 expert labs, I think, including me, 3 of them are present here. They have generally very different preparation schemes. Some of them were already dealing with gases before. Others had to think how to do this, because usually we work with solids. Huh? So some collect really all of the hydrocarbons, others only some, and some did that on purpose, others did that accidentally. Yeah? So, and some even split the gases into the various components, so they could do the whole and also the pure CO2 or the methane or the non-methane hydrocarbons and anything, and they did that purposefully. Some methods, however, select accidentally. And just to give you, I don't give you the details of it. Here are 3 of the labs with the schemes that, of course, they provided for this ring test, where you can see you can do all kind of tricks with cryo traps, with zeolites, you name it, and you can do different things to select only the methane, the pure gas, or the higher alkanes, or combinations of the like. And some are really accidentally not taking everything into account, and other ones are doing that on purpose. Right, so here's the whole table. You can see the carbon fractionation intended. If there is an empty space, it means there was no fractionation intended. Sometimes that worked, and all the carbon was indeed produced and given to the radiocarbon measurement. Others where it happened accidentally. And those 3 here really included all carbons. That was the intention. Now here's the results then for the full combustion, so the 3 that really show all the carbon included. The green ones are the biogases, and you see the values for gas D and gas E. These are the averages. And you see indeed biogas D is slightly higher than biogas E, or I should say it the other way around. E is a bit lower than D. And that indeed means that E has a fraction of fossil fuel there. And Rice actually found out that this facility producing biogas, they are allowed to, when the process is interrupted, to admix natural gas. And of course, when everything goes well again, they start with biogas again, but there is still a possibility of a fraction of natural gas, and indeed that was the case here. Now, based on these values and the mixture that we know very carefully, you can calculate what you would expect for the mixtures, and those are shown here. So B and C are based on biogas D, and A is based on gas E. Now, if you take a look here, you see that in general there is good agreement. You can also see that the reported uncertainties by the labs taking part in this ring test are probably too low, and that's not because the precision of their radiocarbon measurement as such is not good enough, but because the pretreatment brings in uncertainties that are not fully reproduced in the uncertainty that they provide. And indeed, gas E is likely not 100% bio. That was a side result, not intended, but it was kind of funny that that came out so well. Yes, so if you look at the various preparation routes, as I said, some collect all of the carbon-containing molecules, and others only some, and some do that on purpose, and some do that accidentally. And in this scheme, you see one of the mixtures, the one with 45 bio, the green bar to the left, and the measurements, that is the labs that supposedly collect all the carbon-containing molecules, whereas the 4 red points to the right, you see there is selectivity of the carbons. And again, some do it on purpose, others do it accidentally. And only the rightmost point here is the one where the methane really got isolated exclusively and on purpose. And you see that value, well, is in reasonably accordance with what we expect for the pure methane. The mixture in brown, where you have the mix of methane plus the fossil ethane and the fossil propane, would land somewhere where the brown curve is. So you see that 3 out of these 4 points, they kind of are dragged towards there. There is not a pure methane measurement, but there is certainly not a all carbon measurement either. So this is really something that came out of the ring test that we have to describe better for making this a valuable method. Right. As we all know, the radiocarbon content in the atmosphere changes over the course of the years, so the 100% bio level also does that, and it provides a systematic uncertainty. Here is the curve based on the Jungfraujoch, so the high Swiss alpine station measured by the University of Heidelberg for decades already, as the kind of highest radiocarbon value that you will find in Europe. It's the mixed high troposphere there. That's kind of the best value, the highest value, if you like. The blue one is from our station, Lecce, just north of Groningen at the Waddenzee coast, which is a background station, but it's a continental background station that stands for where usually the crops grow. So that's what is well possible that crops and all the materials that produce the biogas have as a content. Now what we do then, we realize, of course, the value that we choose depends on the average growing year. Well, the 2 biogases we have are recent. If you would have stuff from trees, for example, then of course you would have an average over a much longer period. But in this case, that is pretty specific. And it depends a bit on the region of growth. So these were European, these were Swedish actually, so we think these are representative. Now then, the high-end value that we take is the April to October average of the 14C value of Jungfraujoch. That's the growing season average there. And the low-end value we take as the 14C April to October average of our Dutch station Lecce. And for the year 2018, that's the year where these biogas were produced, that's the range between 103.4% and 101.1%. So you see there's a bit more than 2%, if you will, uncertainty range there. And then we calculate the minimal fraction of Bio-C as the measurement minus 2 times sigma divided by the maximum reference value, and the max is of course the opposite, so the highest possible 14C measurement divided by the minimal reference value. And that gives the range of this method for the bio percentage of such a gas. Now then I already showed the results in terms of radiocarbon, but now I'll show them in terms of the fraction bio. Here's what you get for the two biogases, number D and E. You see this 14C value repeated again. You see they're systematically different because the uncertainty is something like 0.3%, K equal to 2 sigma. If you then calculate the biofraction, you see these ranges, or if you express them as a value plus or minus an uncertainty, you get 99.5 plus or minus 1.4% for biogas D, which indeed is fully bio, and for biogas E, it is a bit of like 2% lower, 97.3. So once again, indeed, there is still a tiny bit of fossil fuel there. Yeah, so that's what I said. Indeed, gas E appeared to contain something like 2.5% of fossil gas, and that was properly detected. And if you then look back on the GC analysis, you see that the appearance of these non-methane hydrocarbons, so the higher alkanes, indeed hints to the presence of natural gas, because natural gas always contains those, and biogases hardly ever. Quantification, however, would then be very difficult, because in the different natural gases, these NMHCs vary. But they give a hint. Now, and here's then the result of the ring test. So for mix A, B, and C, you see the fraction bio 72, 94, and 45, as kind of expected. Look at the uncertainties that we get from the value. So one would say this is a very reliable and accurate method for fuel gases containing methane or methane and other hydrocarbons. This works. And the uncertainty is better than 2%. And the majority of that uncertainty is systematic. It is, by definition, caused by the 100% bio value that we take. What is crucial, and that was indeed also this ring test showed, sample preparation methods should really include all carbon, including the CO2. Even though the CO2, of course, doesn't take part in the combustion, it is still emitted to the atmosphere, and for the atmosphere, CO2 is CO2. So that also should be in this total package of biofraction. And what we saw is that not all, even the experienced radiocarbon labs, are per definition, say, prepared for dealing with biogases, which is logical because their preparation lines are simply not made for those, or at least not for all. All this can lead to a design of such an ISO standard, which is, of course, similar to the other ones. Only the preparation part should really be defined differently here. So we are going to write a test method for 14C-based verification of biogas, biomethane, mixtures of natural gas with unconventional gases and renewable gases. That's a whole line, but these legal documents like these very specific long titles. And it should also be applicable for other fuel gases containing, well, one hydrocarbon or mixtures, or even mixtures with CO2 and CO, as I just explained. They have a lot in common with the existing 14C-based standards, like the definition of the 100% bio, which is crucial for the method, of course. And also, I didn't pay attention to this, but measurement precision, including the pretreatment, is a thing. And also a thing that I didn't mention, the carbon-13 correction is a bit tricky if you mix fossil with bio, because fossil, after all, doesn't have any C14, so correcting with the carbon-13 value for fossil corrects the bio part, whereas it shouldn't. Anyway, we published on this a couple of years ago. What is different? That is the sample pretreatment. So we have to prescribe a way of performing and testing complete conversion of all the gas components. Yes. To finish, I decided not to sing because the contrast with the fantastic music this morning would do pain in your ears. So instead of that, I present a cartoon by a Finnish cartoon artist who makes a lot of cartoons on energy transition, environmental issues, and is worth looking at. And this is the one that is appropriate here. Thank you.
We have time for a couple questions. And there is somebody there. Somebody.
Thanks, Haro, or should I say Volare? But we did a study on a wastewater treatment plant trying to partition the various carbon emissions, and we got a surprise. So I guess this is a cautionary tale in that we measured activities in, I think, some of the primary sludge in particular of 200 PMC, which we didn't have a great explanation for other than that it was likely to be 14C labelled compounds in the municipal sewage systems. And if you have a look at what's available, it's alarming. There are hundreds, if not thousands, of 14C labelled compounds that are available and which don't need any licence to import and use. And a lot of them end up in the municipal sewage system. So when biogases are made from wastewater sludges, there is the potential that they might contain such hot carbon.
Yeah, fully acknowledged, and it can even be worse. If you can make money, then everything is done, allowed or not. So you can even think about deliberately masking a mixture of fossil by adding a bit of radiocarbon. The only thing that helps us is that it is very careful work, and for industry who have to hide these processes, probably also still too expensive and too risky. But you're right, the accidental mixture of anything radiocarbon labeled would indeed spoil the method, sure. Yeah.
And Walter. You mentioned biogas. Can you comment a little bit on biofuel? Because biofuel is something which is going to come, apparently. Yeah? Is that going to play a role in replacing fossil fuel?
Well, the role will always be minor in the sense that it will certainly not take over. We're talking about a few percent, which includes biogas and biofuel. But for example, if you think about aviation, I would not know anything else that can replace our kerosene than biokerosene, for example. Now, I'm not the brightest of all minds, no doubt, but still, that's one way that the biofuels go to. Biofuels are actually covered in one of the other standards already. Mm-hmm. Yeah, so that's done. I mean, our petrol here in most parts of Europe contains already 5% biofuel. Mm-hmm. Yeah.
Okay. That's a very interesting presentation, and I want to add, when I work at Geochron, we have a case when houses in New Hampshire suddenly started blow up, and they discovered it was built on the landfill. And not so far from this place was underground gas storage. And it was actually a case when they have to decide, is it come from landfill or from gas storage? Gas storage certainly natural, and landfill is biogas. And it was about 75% of modern.
Yeah, right, sure.
Yeah, mostly landfill. Thank you.
I see you.
Oh, sure.
Yeah, can you, or do you have an idea about what kind of, or what level of uncertainty we can expect with this new protocol? You know, because the ASTM protocol set about plus minus 3% absolute uncertainty for all the issues you were mentioning about the declining bone peak and the uncertainty in the fractionation correction. And they say that in your case you see plus minus 1.4. So it's probably something around that value, plus minus 2%, something like this.
The 1.4 is already, the main source of uncertainty is the 100% bio level. And of course that uncertainty, its influence of that uncertainty goes down if the level of bio goes down. So that's why you see for the 75% 1.4, but it scales. And so yeah, I think it depends very much if you know quite well where your material comes from, like in this case. I think the 100% bio definition is quite reliable, whereas if you have no idea and there can be wood involved, then the uncertainty grows. There's nothing you can do there.
Okay, thank you very much.
Yeah, okay, thank you very much. Yeah. Are you going to sing? Next presentation by Renata Joe. It's from Brazilian laboratory in Niterói. Is it correct? Thank you. And presentation is handling liquid biofuel samples for biogenic fraction determination at this laboratory.
Okay. Good afternoon, everyone. My name is Renata Jo, and I'm doing my postdoctorate research in the University from Bahia in Brazil, in the new radiocarbon lab called LAPAC. But I did all my postgraduate study in the radiocarbon laboratory called LAC with Professor Akita Macario in Rio de Janeiro, Brazil too. And I continue work with her in some projects and research, but today I will talk about methodological work. One minute, better here. And today I'll talk about methodological work, and thank you. In the big project we have in LAC called, I use biofuel samples, and the name of this project handle liquid biofuel samples for biogenic fractions determined at LAC UFF. So you know the AMS technique, it's a great sensitive perceived technique and can use for determination biofractions and for such biofuels. And that can differentiate chemical identical materials through the analysis of biogenic and fossil carbon. Biogenic source have a contemporary isotope ratios atmosphere, so have radiocarbon, while fossil source, for example, petroleum, do not, because all the radiocarbon decayed. So we can use this technique to determine the biofractions, such as biofuels. In Brazil, we don't have an entity to monitor these biofuels. You do not have yet approved laboratory to monitor this product. And LAC UFF is the only radiocarbon laboratory with AMS in Brazil. And we try to help the government to improve this scenario because we have a lot of tax incentive to produce this biofuels or bioplastic, but we don't have inspections. So these two photos, the LAC UFF, we have a sample preparation lab and a single stage AMS. And this is a photo from LAPAC, the new radiocarbon in Bahia, another state in Brazil. Now I will show you the methodology we use to do these biofuel samples. We basically choose 4 different types of fuel. Common found in some cultures, gasoline, ethanol from sugarcane, B100 is like a vegetable oil, and diesel. We choose 2 groups, volatile and not volatile, with biogenic source and fossil source. The idea is cover all the different types of full samples because we have, how can I say before, a big project, and we work with full samples with very low PMC, and it's very important be accurate and precise. So basically the steps for preparation is 3. The first is sample preparation, the second answer the samples in accelerator, and the third is analyze the results. For the sample preparation, we have basically the combustion, purification of CO2, and the characterization. But for this, before the combustion, we have a handling process, and step is very, very important too. So basically this step is first sample handle for preparation, second is preparation of combustion tube and vacuum line, we have a combustion, purification of CO2, graphitization, and finally pressing the sample for measuring the EMS. So, how can I say before, we have 2 groups volatile and not so volatile. For example, diesel is not so volatile, and I can handle it using glass pipette. But the problem is when I have a very volatile sample and the glass will not work, what can you do? What can you use? So I test using glass pipette, automatic pipette, plastic and glass syringe, and I show the result of this test. So how can I say? I have 3 tests in this case. The first is the handling using glass syringe, automatic pipette, glass pipette, plastic syringe. The second test was using temperature trap. In this case, I used liquid nitrogen at minus 196 degrees Celsius, and the second trap is minus 50 degrees Celsius. The third test, I froze the samples before do the vacuum in the line. I test using fumer hood and glove bag, because when I have, how can I say, very low PMC, when I frozen the sample, for example, if I use liquid nitrogen, when I froze, it's possible frozen together the carbon present atmosphere, and for full samples with very low PMC, this can be a contamination factor. So only show the process, in this case not volatile sample, we have a combustion tube with reagent silver and copper oxide, and we have an inner tube, and I put the sample, in this case for not volatile sample, I use glass syringe. I weigh around 2.5 milligrams full sample, and I froze the sample. I can use liquid nitrogen trap or minus 50 degrees Celsius, and put in the vacuum line, to the vacuum, and seal with a blowtorch. For volatile sample, the idea is the same. I use the combustion tube with reagent silver and copper oxide, and I have an inner tube. In this case, with very volatile sample, I use glass syringe, and I froze the sample in a glove bag with a net atmosphere. In this case, I use nitrogen atmosphere, and I connect this tube in a vacuum line, do the vacuum, and seal with a blowtorch. And I do the combustion of 900 degrees Celsius for 3 hours. And after that, I purify the CO2 in the vacuum line. I use 2 temperature traps, and the gas, after purify, I transfer to graphitization tube and seal together a tube, and I do the graphitization. In this case, a zinc reduction. And when the sample are in graphitized, I press in some kettles and put in the wheel and measure in the MS. This is the AMS in Lecce, and for determination the biogenic fraction, I use the STM D6860. Now I show the results. Only to remind you, I present 3 tests, 3 results. The first in handling, the second in temperature traps, and the third is experiment I froze the samples. For the first test, I use volatile and not so volatile sample. I have a B100, is a biogenic source, and I use glass pipette, automatic pipette, and glass syringe. For automatic pipette, the results PMC was around 70. When I compare with the another test, the results was around 95, and the value spec is 94.5. So in this case, the automatic pipette for the worst. For diesel is a fossil source. I use glass pipette, and the results PMC was around 1. and the expected value is 0 because it's a fossil source. When I compare with another result, automatic pipette and plastic ring, the difference is considered. For gasoline is a fossil source and very, very volatile. The result with automatic pipette was around 6 and 3, and the plastic ring was around 3, and glass pipette was around 2, and the expected value is 0 because of fossil source. And the best in this case was using glass pipette, but I have very difficult to manipulate this sample because it's very, very volatile. And I will show in the next test, number 3, I use glass ring, was the best result. For ethanol, it's very difficult to manipulate, and I use only automatic pipette, and the result was around 70, and the expected values is 100. For the second test, I use only not volatile sample, diesel and B100. In this case, I use glass pipette, and in this case, the temperature trap I test liquid nitrogen and minus 50 degrees Celsius. For B100, the results, the liquid nitrogen and minus 50 degrees Celsius was not so different, but because the expected values is 94.5, but for the diesel is a fossil source, when I use a temperature trap minus 50 degrees Celsius was slightly better than the nitrogen, like nitrogen. For the third test was the element I frozen the samples before do the vacuum in the line. In this case, I use glass syringe and I use only gasoline because very volatile and fossil source. In glove bag was the best, and when I compare the Fumerhood, because the PMC expect was 0. So for conclusion, now we have 2 new protocols for liquid samples. For volatile sample, the best was use glass syringe and freeze with like nitrogen in a glove bag. And for not volatile sample, the glass pipette and temperature trap minus 50 degrees was the best. So how can I say before? We have collaborated with some company and they send full samples with partial with biofuel and very, very low PMC. So it's very important we have accurate and precise. And so in order to, the idea is to cover a variety of fuel types and their variation, mainly for fuel with low PMC. So I'd like to thank everyone here, and some agents helped me. And here's some reference I use. And this is, thank you so much. And sorry I'm nervous, but it's okay.
Thank you. Okay.
Oh, water. Thank you.
Yeah. That was a very interesting presentation, and we have time for the questions. Any question? No, okay, I will start. I have a question. You show us ethanol, which has something like 70% of mother.
Yes.
How it's come from? What's the origin of this ethanol?
It's from Brazil. The PMC expect was 100, and because automatic pipette we show a very, how can I say, contaminations, no work in in biogenic source and fossil source, the contamination is
Do you think this ethanol was growing in a field, or it was a mixed synthetic ethanol from petroleum and natural?
No, it's biogenic source, only sugar cane, this case.
Yeah, that's actually look like a mix of synthetic ethanol made from petroleum. That's about 30%. And the rest is bio. I don't know, whatever, it's some grasses or corn, whatever was used for fermentation. Yeah, and actually in Brazil, it was not a single case, because when they have low crop on corn, they made it from petroleum and say it's biofuel. And your radiocarbon technique can help to... Yeah, Walter.
In Brazil,
I don't know what the worldwide situation is in this. Are there any countries who have already certified places to determine whether the fuel is or biofuel is, what the percentage of biofuel is, and so forth? Is there anything like that going on, or what is the situation in your country?
In Brazil now we have a lot of incentive to produce this type of product, not only biofuels but bioplastic too. The problem is we don't have an entity to inspect this product, so I can produce biofuel and say, this is 100% biogenic. But how can I prove this? I don't inspect, I don't monitor this process. So we don't have yet approved lab to certify this type of product. There's a problem, big problem in Brazil, and try help the government to prove this scenario. Is a big problem, but I believe it's
okay.
One more question.
I have a comment, maybe. This 70% that you're worried is a mixture of modern and old. Can you make a biofuel with algae? If you have a
they're cheating with that. They make it from petroleum and add to the gasoline, say 10% of biofuel there.
Instead using corn and algae, which the algae will be modern, but with reservoir age.
No, petroleum ethanol may be even cheaper than plant ethanol, you know?
I would like to comment what Walter was asking. We are doing here, in Italy at least, this is what we are doing here in our lab. We are measuring biofuels on a routine basis, mainly for different Italian petrol companies, mainly for kerosene for aircrafts. The problem is that usually the bio concentration is quite low, and this, you have some more problems in correction for background because you have 1-2% or even lower bio concentration, and this raises some problem in the calculations. But we are doing it on quite routine basis.
Okay. Any more questions? Thank you.
Thank you so much.
Yeah.
That looks like my presentation. So. What's Monty? Are we having a break or? I'm not sure. We could.
Hello? The other one. Hello? Can you hear me? Yeah? Okay. So we have Monty Ochocki, who's going to talk. Sorry. Can you hear me now? So we have Monty Ochocki, who's going to talk to us about a pre-treatment technique, acid-base acid with step combustion.
Thank you. Hello, everyone. Thanks for having me here. It's great to be here in Lecce. I'm going to be presenting some experiments that were completed kind of as a side project to my PhD, which I finished about 18 months ago, and since then I've been working as a chemistry technician at the Radiocarbon lab in Oxford. And the experiment I'm going to be presenting is focusing on the radiocarbon dating of charcoal. My background is in archaeology and environmental science. This, as I said, this is a sort of a smaller project of my PhD. So, as everyone in the room probably knows, charcoal, since the invention of radiocarbon dating, has been recognized as an excellent material for dating. Has a very high carbon content and is relatively stable post-deposition in archaeological and environmental contexts, particularly in comparison to other materials like bone or wood. So quite often where dating those materials fails, charcoal might succeed. And as I said, it's frequently recovered in archaeological and environmental contexts. So it's sort of ubiquitous. And it's also terrestrial in origin, so it doesn't sort of suffer from the complications of reservoir effects. But despite all those kind of qualities, it's not immune to contamination or exogenous carbon being included in the material. It's very porous with a high internal and external surface area, and so is susceptible to contaminants from groundwater table movement or microbial activity. And so for that reason, we typically pre-treat charcoal in Oxford. We use these two methods. On the left is ADA, so acid-base acid wash. The first acid wash is to remove carbonates from sediment-derived carbonates. The base wash then targets sort of loosely bound organic compounds, we might call humics. And then the final acid wash is intended to remove any CO2 absorbed during the previous base step. This is probably all very familiar, but I thought I'd just sort of cover it anyway. And so for older charcoals, we use this method ABOX-SC, which stands for acid, base, oxidation, and step combustion. And generally we apply this ABOX method to charcoals suspected to be older than 25,000 radiocarbon years old, or charcoals that are heavily contaminated. And in general, the ABOX method is a more aggressive pre-treatment. So comparing the two methods, over the last sort of 15 years, there's been a number of studies comparing these two methods and showing that ABOX can be in certain contexts more effective. So this is a figure in the black is ABA dates. In the grey bar down the middle is a known age tephra, and the grey are ABOX dates. And so each sort of row is a single paired dates for those samples, and these are all found below the tephra layer. So what this figure shows is that the ABOX dates are generally in better agreement with that tephra layer. So sort of unpacking those differences a bit further, I can identify three differences between ABA and ABOX. The first is an increase of acid and base wash concentrations, quite a stark increase. This oxidation step using acidified potassium dichromate, replacing the last acid wash in ABA. And then also this step combustion step after wet chemistry. And so in thinking about why the ABOX might be a more effective pre-treatment for these older charcoals, there could be sort of three reasons here, and they could also be interacting. So you might also ask, why not just use ABOX all the time? And one reason not to is that it involves this potassium dichromate, which is hazardous in many ways and sort of looks hazardous as well, and is a bit laborious to work with in the lab. And so one of the motivations in the experiment I'm presenting here was to see if we could sort of avoid using this chemical in future. And some other downsides of ABOX are that generally we need a higher starting mass, a high amount of charcoal, so which is not always possible. Also, it has a very high sample failure rate overall, particularly during the strong or high concentration base wash. As I mentioned before, the potassium dichromate is difficult to work with. And it's generally more involved, so we only are working on 5 to 10 samples at once, meaning we generally have a lower throughput with ABOX. So the sort of fairly straightforward experiment I designed was to investigate particularly this step combustion step, which is quite similar to the ramped oxidation methods that were mentioned earlier today. And one of the papers that kind of inspired this experiment or sort of motivated it was here, showing that perhaps ABA-SC for these three samples here can produce ages similar to ABOX-SC. So perhaps suggesting that the step combustion stage of ABOX is the sort of important part. So the samples are sort of selected from the Radiocarbon archive in Oxford were previously shown to have these differences between ABA and ABOX dates. And they're from a site in the north of Italy called Fumani. And these blue stars here are on the stratigraphic diagram are where the samples came from. And these are upper Paleolithic or middle to upper Paleolithic layers, so at the sort of transition there. And this paper at the top is the sort of paper that showed these differences for these charcoal at Fumani. So here's a table of those differences. And just to sort of reiterate the basic idea, on the left here are the ABA dates, on the right are the ABOX dates, and the idea is to sort of take these ABA excess pre-treated material, apply a step combustion step to it, and then compare those dates to the ABOX dates. And the step combustion method in Oxford looks like this. So we take around 20 milligrams of freeze-dried ABA-treated charcoal for this experiment, put it in a crimped combustion tube, plug the tube with silica wool, evacuate the tube, add 600 millibar oxygen, and then heat to 630 degrees. So, and then after this, the remaining material we combust and graphitize in the routine way. So here, looking at the results of this experiment, so I should say as well the ABA dates were repeated to sort of account for any differences between their original dates. Some of these samples had been in storage for about 20 years, and so we repeated the ABA dates. So the x-axis here on the larger plot, each column is a separate sample, and in red, blue, and green are the ABA, ABA-SC, and ABOX-SC dates. And consistently, the ABA-SC dates are older than ABA, but younger than the ABOX-SC dates. And so in general, that suggests that the sort of wet chemistry of ABOX is also an important factor, at least in this, in the context of Fumani. And then as a way to sort of compare these dates and give them a kind of common method to compare between them, this is a sort of measuring the proportional effect of step combustion on this ABA material expressed as a proportion of the inferred contaminant removal by ABOX. So if the ABA-SC date was the same, we'd see a value of 1. And so the dotted line is a mean of these values, and tentatively suggests that step combustion in this case can account for about 50% of the contamination removal by ABOX-SC, but there is some variability there as well. And then on the bottom is stable isotope values, which aren't terribly consistent, but in most cases suggest enrichment after step combustion. And as I said, there was also this sort of opportunity to test the effect of up to 20 years in storage, or 27 years in storage. And in general, there was no consistent pattern between the ABA dates that we measured. Only one surpassed the chi-squared threshold we use to sort of highlight differences between radiocarbon dates, and that was the sample that had been in the archive for the longest. And the stable isotope results were remarkably consistent. And so the conclusions, as I said, step combustion has a significant effect in contaminant removal. We do see a difference in the dates after step combustion of ABA material. Our long-term storage didn't show any consistent pattern, which was good news. And I guess less good news is that potassium dichromate is important, or at least and/or increased acid and base concentrations are shown to be important. So we'll carry on. And in future, I would say it's still unclear why ABOX is sort of producing these older dates in certain contexts. I think it would be useful, as in some other papers, to use elemental analyses or FTIR along the way to understand what's being removed, how the material is changing along the way. And also, in the case of Fumani, these were unknown age samples. And so there are examples of known age samples, or another method would be to sort of spike the samples, contaminate them with a known contaminant. So, yeah, and volare.
Thank you very much. Very impressive indeed.
I just have to go for it.
Questions?
Okay. Thanks for the interesting talk. I may miss you, but the thing is, when you look at the delta C carbon 13, most of the case when you have the younger, the older age, you have the lower or higher delta C carbon 13, right? What does it mean?
Delta 13C.
Yeah, what does it mean for? Does mean the contamination have a lower delta C carbon 13? What is mean there?
I mean, this general pattern would indicate, I would say, a sort of preferential combustion during step combustion of the lighter material. It might suggest as well that a sort of separate fraction is being removed during the step combustion.
Does it point out, what kind of contamination because you have lower delta C carbon 13?
The contaminant has a separate delta 13C signal, you mean?
I just wonder, what the meaning for low carbon, that's mean contamination from a lower carbon 13 compared to the real age, right? Yeah.
Yeah.
Okay. I just wonder, what it mean into environment,
Yeah, they're not sure. I might have a separate, here is some sort of more detailed data on the step combustion. We also see a much higher carbon content after step combustion, a reduction in mass overall. So it's certainly changing the material, but as to how or exactly what's happening.
I wonder why you chose 630 degrees. That's first part. And second, why you call it step combustion? Because you have only one temperature. Friendly question.
Yeah. So it's the sort of stepped combustion method refers to the sort of original design of the ABOX SC method, which I think was 1999 it was sort of developed. In those experiments, there were 3 temperature steps. In the lab, we sort of disregard the first temperature step, so that I think it was 400, 600, 900. So we don't do the 400 step. We step combust the material at 630 degrees, and then effectively the last step we do by the routine combustion at 900 or 1,000 degrees.
So you do 2 temperatures, therefore.
2 temperatures.
I see.
Yeah,
Okay.
yeah,
Gotcha. Yeah.
As far as I know, Tom Hyam has corrected some of his earlier measurements in connection with the Neanderthal to older and older ages. So the question is, do we have to believe that the older ages are the more correct one now? Or can we not do this? Can we not conclude this yet?
Yeah, as I say, the sort of downside of this experiment is that the Fumani samples are not known age and and there's no tephra at the site that's been found yet that can confirm that. So I guess the kind of confirmation of the ABOX dates in this case were given by comparison to dates on bone. So there was a kind of, I guess it's sort of independent method of by comparison there. But I do appreciate your point as well that it doesn't necessarily mean that sort of older is improved contaminant removal. Yeah.
Thank you. Thank you.
One more.
Thank you. You said you lose about 50% of samples if you apply high concentration sodium hydroxide or whatever base you use. Did you try to avoid this step and after acid treatment to do oxidation?
So there are some other experiments that I believe are unpublished at the moment that were missing the base step, so AOX, and the downside there is still that the potassium dichromate needs to be used in the lab, so the sort of motivation for this was to find a simpler method. But if I can sort of cycle back to those three differences, really exploring these differences between ABNA and ABOX could quickly kind of scale out into quite a big experiment. And there's also the other variable of where the samples come from and the different environmental contexts that they could be from. So I sort of chose to focus just on this one aspect to
I'm asking because potassium dichromate will oxidize humic acid, which is actually you try to extract with base. And maybe it will preserve your samples. I don't know. I just asking if you try to do this.
It's definitely the base step where most samples are lost. In ABA as well.
Okay, thank you.
Very, very, very short.
First is a comment. Your ABA treatment seems a little bit weak. The base is very weak, so it seems a little bit unfair compared with the ABOX step combustion. I'm familiar with the ABOX because I worked with Michael Bird before, exactly with this treatment. And the second thing is blank correction is important in terms of sample processing. So you didn't mention any blank for your correction. So can you comment on that very briefly then?
We did repeat we sort of routinely use background charcoals, and I didn't show that data. I did the same as went to the archive, got the already ABA treated material and dated those as well, and we saw no change. So I didn't include those as a. I thought it would sort of complicate things because we didn't see any difference between the steps. But yeah, we sort of processed the standard in the same way alongside the steps.
Thank you very much, Monty. So next talk, Kai Nakajima, who's going to talk to us about flow cytometry.
So, okay, thank you. So I'm going to talk about pollen separation. So I'm interested in dating pollen, specifically pollen extracted from lake sediments. And I'm going to show you how flow cytometry can be used to do this. Pardon? Hello? No, sorry. So I'm interested in dating pollen, specifically pollen extracted from lake sediments using a technique called flow cytometry, which is a relatively well-established technique, originally in the medical sciences, but now slowly finding its way into the earth sciences. So the problem with radiocarbon dating lake sediments is that the carbon found in sediments comes from various components of the carbon cycle, which all may be characterized by their unique 14C signature and their history of transport and recycling processes. So we have a lot of pre-aged organic carbon in lake sediments, as well as those marked by reservoir effects or hard water effects. And a solution to this is to target a specific component of this of the sedimentary matrix, and the most straightforward way is to do this with macrofossils, usually from terrestrial plants. But the macrofossils are often too scarce, so chronologies reliant on them are often too unreliable. So people early on suggested that pollen are maybe the ideal alternative to macrofossils. So pollen, which you can see here, are usually well preserved. They are composed of a polymer that's chemically very inert, and you can find them practically everywhere. They come in various shapes and sizes, but typically one pollen grain constitutes around 1 nanogram of carbon, so you need a lot of them for radiocarbon dating. At the same time, they are established markers for past vegetation coverage. So if you can get a radiocarbon date on pollen, you can get a proxy-specific and source-specific chronology. So traditional approaches for extracting them have proved to be not suitable for it, mostly because they are either too time-consuming or don't achieve the purity. And flow cytometry can overcome these issues. So this is the general workflow. So first we do some chemical pre-processing. We take around 1 gram of dry sediment, treated with hydrochloric acid, sodium hydroxide, and hydrofluoric acid in order to remove carbonates, humic matter, and silicates. This results in a particle mixture of organic debris, which is still dominated by other particle types. We take this particle mixture and introduce it into a flow cytometer. So this flow cytometer takes suspended particles and focuses them into a stream of microdroplets, and a laser analyzes each particle individually and for its optical properties. And when these optical properties meet predefined criteria, a charge is applied to this droplet and it gets deflected into collection tubes. So with this step, we are removing all the other organic particles, and we are left with a sample that's practically composed of only pollen. So we take this sample then for combustion into an EA-coupled AMS system, but also because we are dealing with relatively small sample sizes of around several tens of micrograms of carbon, we need to do some blank corrections. So during flow cytometry, we are analyzing around 1,000 particles per second, and we are analyzing for forward scatter, side scatter, and 2 different fluorescence intensities that are emitted after excitation with the laser. And these properties reflect the particle size and surface complexity, as well as its molecular composition. So we can define the areas in the parameter space that's dominated by pollen. So in blue and red, these are the regions in the parameter space dominated by pollen, and all the particles that are in both regions are getting deflected and for collection. Usually, sorting recovery is around 80% or higher, and we can balance the sorting purity with the duration of the sort. However, differentiation between different pollen species is not possible because there's too much of an overlap between pollen of different plant species, and there's no clear boundary between pollen and other particle types. So in practice, if you take a pre-processed pollen sample which has like around 1% of pollen concentration, and we want to extract 50,000 pollen, then this results in a sample of around 50 micrograms carbon, and in the highest purity setting, it takes around 10 hours of sorting. So here you see a comparison of before and after flow cytometry. So on the left side, just the pre-processing, we have a lot of plant debris and other organic debris, and pollen account around 5% or less of the entire of all the particles. And after the sorting, we have like pollen purity of around 95% or higher. Purity in terms of carbon mass might be even higher than this. So because of the small sample sizes, we have to do a blind correction, and for the blind assessment, we've included processing standards alongside normal part samples for the entire procedure. So here we are tracing the fossil contamination with modern pollen. Each color represents a different processing batch from which I've subsampled several samples with the flow cytometer. So I've done the same with carbon dead pollen as well for tracing the modern contamination, and in total we get around 1.34 micrograms of carbon constant contamination, regardless of the sample size or the batch. And this data we can now use to correct all the 14C data of our actual pollen samples. So here I compare how our pollen 14C dates perform against tephra dates of known ages. So in blue you see the reference ages from the literature for tephra events from tephra layers of volcanic events across 10,000 to 13,000 years ago, and I sampled 2 centimeters of sediment around each tephra layer. So you see in the tephra our pollen dates in gray, and the match for the oldest 3 samples from the very top to the match is quite good. Even for the last one, it may not look like it, but the age estimates just are barely touching at the 2 sigma intervals, but there's a good agreement within the 3 sigma intervals. Unfortunately, because of how the calibration curve is shaped during this time interval, it doesn't allow us to really determine whether our pollen age is actually older than the reference tephra age or not. So for the next record, I compare the pollen dates against macrofossil 14C data and TOC for a lake record located in Sweden. And here we see that pollen, macrofossils, and TOC generally follow the same line with some age offset. If you look closer to it, so now the difference in radiocarbon ages between macrofossils and TOC and pollen and macrofossils, we see that in red, the TOC is systematically older by around 300 radiocarbon years. Makes sense. For the pollen, however, we see a huge variety actually in the age difference between pollen and macrofossils. And for some, there is practically no difference, the match is perfect. And for some, they are like barely overlapping within the 3 sigma intervals. And so if you look on average, the pollen are around 150 radiocarbon years older than the macrofossil counterparts. And the most plausible explanation we have for this is that pollen are getting resuspended within the sediments within the lake by events such as winds, and they are resettling above the less mobile macrofossil counterparts, which then accumulates it into an age bias between those two radiocarbon targets. And one of the reasons why we think this is the best solutions, the best explanation is that for the oldest part where we have a really good match between pollen and macrofossils, the sediment is composed of primarily clay, whereas for the rest of the record, it's composed of detrital getter, which is more prone to resuspension than clay. So we think that sedimentary processes may be a cause for an offset between macrofossils and pollen. So in summary, I've shown you that flow cytometry can be used for separation of pollen, and we can achieve quite a good separation with a very low contamination actually. So we can measure pollen sample sizes of around 20 to 30 micrograms. Pollen data that we get are generally in agreement with tephra and macrofossils, but at the same time we see in some instances offsets between macrofossils and tephra, which may reflect delays between the formation of pollen and their final deposition in lakes. So this was only one example of how flow cytometry can be applied, and there's a huge variety and open research field for how this could be used for other particle types such as coccoliths, algae, and spores, and other sediment, other particle matrices such as suspended particles or sediment trap samples worked as well. So if you're interested, come see my poster on coccolith 14C analysis tomorrow. And thank you very much for your attention.
Thank you very much. Are there questions from the floor?
Two questions. One, which suspension fluid did you use or solution when you do the flow cytometry? And the second is, any reason why aquatic pollen, since you're doing lake sediments, should not give some older ages? Because you say you cannot sort.
Yes. So in this case, they're just first the fluid. So it's practically milky water, only milky water, and I add a little bit of sodium chloride to make them chargeable, because you need to charge the particles, droplets. As for aquatic pollen, so in this case, the pollen record was completely dominated by trees. So that's the reason we think. And even for locations where aquatic plants are more present, it's because mostly because aquatic plants do not produce as many pollen as trees. Especially conifers dominate most pollen records, so they don't contribute too much to the final size, and they are also smaller. So, yeah.
Other questions? I have one quick one. So you were saying about the pollen being older to do with perhaps bioturbotion or resuspension in the lake. But is there a chance that the pollen that's delivered to the lake has been stored in the environment and is aged?
So this was one of the explanations, possible explanations as well. But so one, if pollen were stored in a different compartment in the environment, in the landscape, then you would be able to see it because they would be more degraded. As for in this case, pollen were perfectly clean, so we are suspecting it happened within the water column. Yeah.
Thank you. Thank you very much.
Yeah, we have now a small change in the program because Slava Kuzmin is going to give his talk during this session. Then we have the coffee break, and then for today it's over. Okay? So the last talk will be given by Slava Kuzmin in this session, the last one.
Okay, there we go. Gotcha. What is this? F5 or something? No. Gotcha. Buongiorno. Welcome to Siberia, by the way. So, let's talk a little bit about the mammoths. Yeah. Iconic animals, as you know. That's what it probably looked like. So Mammutus primigenius, so bigger than modern elephant. And they inhabited all, Eurasia, as you know, and more than 200 years of scientific research passed, but still no any serious clue why these giants went extinct. Several kind of hypotheses were proposed: climatic, catastrophic, including extraterrestrial, this whatever young Dryas, bolide or something from the space. Geochemical means suffering of the certain elements at the end of the existence. Anthropogenic, that's human hunting. Infections, some diseases which killed the mammoths. But none of them explain, reliably why they went extinct. Most probably, the most kind of factually based are climatic and anthropogenic hypotheses. Each of course, each has some problems here and some advantages too. Yeah. So we created the database of about 950 direct radiocarbon dates on bone, teeth, and tusks. We avoided tissues because they're often contaminated. So of the woolly mammoths from Siberia and Russian Far East. And then we try to understand, first of all, the spatio-temporal distribution, although it was done before, but anyway, that's some updated. And then its relationship to climatic changes, climatic fluctuations in the last 50,000 C14 years. Yeah. So here's the distribution of direct radiocarbon dates on woolly mammoths from Siberia. As you can see, many dates are concentrated in the north of the region. So that's why people were usually, doing sampling. It doesn't mean that mammoths didn't exist in the central part of Siberia. They did, but less material is available. Yeah. If you see the distribution by latitude, that's the one. So similar to what I showed, about 70% of dates comes from high Arctic, north of 68 degrees northern latitude. In other words, beyond the Arctic Circle. So that's the current situation. We shall take into account. But I think that's not a big problem because area is big and we can still derive some conclusions about spatio-temporal distribution. Okay. So actually we started 20 years ago with dating of the Paleolithic sites and figured out that the average sigma for set of C14 dates is about 500 years. Therefore, plus minus 500 years, about 1,000 years. So we decided to use the 1,000 years increment. So to plot the distribution of dates. So as you can see, the fluctuations is quite big. And what is interesting, does it work or not? Anyway, just see the very high number, 31 dates between 11 and 12,000 C14 years. That's a young Dryas. Just before the mammoths went extinct in a few thousand years, but the amount of them was quite high at the time. Here it is. That's the one. So very high number and then decreased very quickly. And before that it fluctuates, doesn't stay stable, but the small number in the beginning is just because we have less older samples, not just means there were less mammoths, just a degree of study. All right, so that's a distribution. Maybe it is. Yeah. So what we can say that until 12,000 radiocarbon years, mammoths existed throughout Siberia. And after that, very few refugia south of 60 degrees north we have, between 12 and 10,700. And at that time, mammoths populated mostly northern part of the mainland, Arctic, until 9,700. And after that, they existed only in what today are islands. Perhaps some of them were not islands due to the post-glacial sea level rise, but right now they're New Siberia Islands and Wrangel Island. So that's what do we have today after 9,500, so early Holocene, middle Holocene. Here's just last glacial maximum and soon after that. You could see that mammoth southern limit was quite far south. So, okay. Going closer to the modern time, these red circles represent some isolated or semi-isolated occurrences of mammoths, which you actually do not call refugia. It's just south of 60 degrees north. But again, in the north, there are more dates. But when you come closer to the beginning of Holocene or Younger Dryas, you can see only one refugium. That's in 55 degrees north in the southern Siberia. The rest are beyond the Arctic Circle. Taimyr Peninsula, Yamal, and the islands. So that's a real break of the mammoth habitat. And Volchagriva, we are pretty certain we have like 40 C14 dates on this site, and that's the youngest one. So we are pretty certain that's a definite refugium. Why refugium? Because, as I think, from Eastern Europe and Central Europe, we have a few refugia like this too. I think at that time, the mammoth landscape still survived, like grass-dominated steppe landscapes and patches. They still existed, but very fragmentary. That's why mammoths were able to sustain in some of them. But in the rest, it's just, forest arrived and bogs, and that's no mammoth habitat, no dry grasslands, and that's it. So the last time of mammoth existence, the last stages, that's from 10,000 to 8,000, very, very high north, a few in the mainlands, but mostly in the islands, and that's the last stand of mammoths, well known in Wrangel Island in the high Arctic until 3600 BP. Well, that's the dynamic of mammoth disappearance. Another aspect is relationship between dynamics of mammoth population fluctuations and climatic changes. So, turned out, as some people were saying, it's not linear, it's not straightforward relationship. And we used a study by Puzachenko and company and others published some years ago, and we just took only Siberian part of their database, and we added our new dates which they didn't have. So what we did, we calculated so-called average accumulating rate, for each major climatic events, either cold or warm. I'll show you in a second. For normalized for 1,000 year intervals, because some of these stadials, interstadials, they have different lengths, so we have to normalize it. So that's what we did, and that's Muskovitz, Puzachenko, the group from Moscow, they did the same. But they only, they have less for Siberia, but more for the rest of Eurasia. So here, the yellow are interstadials, warmer, like Moishort, Hengelo, Dennenkamp, Berlin-Kalleröd, last glacial transition after LGM, and then, of course, early Holocene. And the blue ones are stadials, like last glacial maximum, Young Dryas, and a few others, established using the mostly palynological data. And this dotted line, that's a very schematic representation of the delta oxygen 18. So again, for each major climatic event, we plotted the delta oxygen 18 just to see the correspondence. And then try to figure out, is there any trends or any correlation between them? So which turned out to be tricky. But anyway, so from the first glance, you could see that usually the number of these occurrences of mammoths for cold and warm intervals, it's not very different from each other. Before 12,000, calibrated, before the Young Dryas. And after Young Dryas, the mammoth quickly disappeared, and that's all related to the warming here. So cooling after 12,000, practically no cold stage after Young Dryas. So, but otherwise, warm and cold, it's pretty similar number, yeah, with some fluctuations, of course. What we are thinking that there is no direct correlation between number of mammoths and the oxygen, delta oxygen 18, which is a kind of temperature trend. Yeah? So what we tried to apply the trend analysis. And we arrived to the preliminary conclusion that the trend is a clear second order dependence, which is a polynomial, which shows increase in number of occurrences during climatic coolings. And then, so we have some very high number of occurrences and try to remove it, considering maybe it's anomalies. But when we got rid of them, it still doesn't change picture much. I'll show you in a second. So the blue, that's the total set of our dates. And you see the R square is 0.82, good number. And these blue ones, which were thinking maybe outliers, okay, we deleted them, and the correspondence even better, 0.92. But if you can project this trend further, it's still this blue stuff will still be on the same line or so. So it's not real outliers. So, but still, we did two kinds of, analysis. And then, so the result is this, that the trend consists of two parts. First, the more mammoths means colder intervals. And then the trend changed. The more mammoths belongs to warmer intervals, which means that the relationship is non-linear. It's just more complicated, and more work is needed to understand, in details and try to different, whatever, models of correlation, correspondence, and so on and so forth. But I'm pretty sure that it was not simple model like it's getting cooler, there are more mammoths, it's getting warmer, there are less mammoths. No. That situation was very different from such a linear thinking. But, well, we are trying to get more information, and that's what just the first results we presented here. Well, any clues why mammoths went extinct? Do you have any? Please, give me advice. Thank you. Grazie mille.
Thank you very much. Questions?
How sure are you that they are extinct completely?
Well, some native people in Siberia still believe they exist. Yeah.
Okay.
Well, we didn't see any living one. For what? 300 years or 400 years of Russian, colonization, so, of course.
Slava, you show the data on the mammoth, and you could connect to Delta 18. What about the distribution of human, distribution of forest, as you say, the
Right.
driven, and put the time, like how long does it take to build a forest? And, we are talking about a natural environment and not...
Yeah, good question, yes. I didn't pay attention in this presentation because of the time kind of limit. But first of all, humans settled the northern Siberia very late. The only one site dated back to 28,000, the only one. The rest are 10, 15,000 only. Wrangel Island, the first humans appear 500 years after mammoth went extinct. So they didn't overlap. Forests usually in Siberia start to dominate at the end of the Younger Dryas, early Holocene. So deforestation started in the early Holocene, in other words. But again, as I showed, this Volchagriva in central Siberia, it's still forest steppe right now. There's a lot of steppes. And probably there was a patch of steppe surrounded by forests or something. Not a taiga, but like a mixture of conifers and deciduous trees. So, but it doesn't look like there's a straight correlation between appearance of forests and the disappearance of mammoths. We actually had a paper in Nature Communications with Glenn MacDonald, 2012, where they put his part of from UCLA. Put all this forest data, appearance of trees, and so on. Not only mammoths, but also bisons and other extinct species. They didn't see any precise trends. But of course, yes, forestation was important because mammoths couldn't exist in the forest here. But again, it comes quite late in Siberia, and humans even later. And what is important, we have in Siberia and Far Eastern Russia, it's 14 million square kilometers, okay? It's double size of the 48 United States. Huge territory, yeah. But we have only 1 or 2 direct evidence of mammoth hunting. Means the holes in mammoth bones, made by spears and so on, extremely few. So extremely few. The mammoth hunting in Siberia didn't affect, seriously the, existence of a population. Very little. The same in Central Eastern Europe. Very few direct evidence. Probably they did, killing some old animals or young or ones which were trapped in the mud or something like that. So human role is, I think, negligible. Climate, yes, more important. But how? That's not an easy question. We are working on it.
If they became extinct because of climate warming, how did they survive the previous interglacial then?
Excellent question. That was asked many times by others, because the last interglacial or Aegean in Europe, they somehow survived. Some people say they retreated during Aegean to some refugee alike, and then they spread back. But no, I don't think it was. In Siberia, again, it's a very conservative region in terms of vegetation. It's huge continental, not many oceans and seas around. Climate is, dry and cold in winter, very hot in summer. That's why probably the landscapes didn't change dramatically during Eemian in central Siberia, for example, like Yakutia today. Yeah? That's why they felt pretty cozy there. In maritime regions like Western Europe, of course, the climatic warming affected much more the vegetation and habitats of big animals. Yeah. So still, this question was not answered. Yeah, why they survived? Mammoth appeared, woolly mammoths, about 600, 700, 800,000 years ago as a species. So it survived several interglacials. Yes, indeed. Yeah, big question. I agree. Yeah, Alexander. Yeah.
Can they survive in the forests?
No, I don't think so.
No.
They were, according to what we found in the stomachs, of mammoths, they were eating mostly grass and shrubs.
Yeah, it's called tundra steppe.
Yes, tundra steppe, or whatever. Yeah.
But
cold steppe.
you have a big peak of mammoths when, in actually, what it's called, Wisconsin bombing, 2932. That was actually some interstitial, which was much warmer.
Yeah.
Maybe even warmer than we have now.
I see. You mean during the deglaciation?
Yeah, but you have a lot of mammoths. I don't know exactly where they come from.
Yeah.
It does not say it. From South Siberia or Northern.
I understand. We can separate it. Yes, well, I mean, the number fluctuates, but that's not a very significant, I mean, yes, there are more, but that doesn't mean they felt better, the environment was better for them than previously. So my idea was try to compare it with the, Greenland ice cores, but there are much more details, Greenland ice cores. And we can, if we will do it, it would be, I think, monkey business, So you have to take the larger climatic units, climatic events in the past. Because, there's 50 years or so resolution for Greenland ice cores and 1,000 for mammoths, incompatible.
Okay, thank you very much.
You're welcome.
And please join me in thanking all of the speakers for this session before coffee.